welcome to Untamed Beyond Boundaries. My name is Ferry. I'm from Science Center Singapore, and I will be your host for today. So, what is Untamed, you may ask? Untamed was born out of Science Center's ambition to redefine guest experience amid the pandemic, leveraging on a multidimensional approach to spark curiosity and self-learning, both on ground and online. This podcast is part of the Untamed Conversations, where we will be conversing with some very special guests about wild and wacky topics around science, technology, engineering, and maths. Also, to celebrate that all that is untamed, we would be giving out two prizes kindly sponsored by the US Embassy of Singapore. All you need to do is to share about your Untamed Challenge experience and hashtag UntamedSG on your social media pages to stand a chance to win. So, in today's Untamed conversation on coffee, we are very, very happy to have with us Christopher Hendon. He is an assistant professor of chemistry from the University of Oregon. Now, he's going to share with us about his experience and expertise in coffee. Ladies and gentlemen, let's welcome Christopher Hendon.
Hi,
Hi,
Ferry.
Chris.
Thank you very much for the invitation to speak with you.
It's our pleasure. So, Chris, so good to finally meet you and be able to have conversation with you about coffee.
Yes, me too. I know that in other times it would have been nice to be there in person, but this is pretty good. So I'm really looking forward to it.
Yep. Well, I'm pretty sure the audience would want to know more about you, Chris. So why don't you tell us more about yourself and how you end up, getting into this whole coffee business?
Yeah. So despite my accent, I'm actually from Australia, and so I originally, in Australia, coffee is a big deal, of course, and so I grew up and I was interested in coffee, but never took it very seriously. I was more of a day-to-day consumer, and I shared that experience and the interest with my mother, who was also really interested in finding good lattes, basically. And so it started there, and then I'm going to show you a little bit in the presentation about how it evolved into being actually one of the main things that I do in my research is to study how coffee can be changed and perhaps improved from a material science perspective. And I think it's a nice topic because it captures the interests of chemists, biologists, physicists, mathematicians, and I've worked with all of them in this journey so far. And, it hasn't been that long. I've only been doing it for about 6.5, 7 years, but you can get a lot done in that time.
Oh, I seriously can't wait to have to hear what you have to say. And I myself, I teach chemistry of coffee class in Science Center Singapore, and I do tell my students, and if you want to make better coffee, if you want to improve, the quality and the taste of your coffee beverage, science is the way to do it. And in fact, without them even knowing, sometimes when you change something in the way in the brewing process, you're actually applying scientific method there. So
Absolutely.
Yeah, really, really excited for this.
That's right. And it's one of the only experiments you can actually drink at the end of it.
That's true. That's true.
Yeah, that's right. Well, I've got as you can see here, I'm in my digital pub because it's Friday night in Eugene, and that means it's Saturday in Singapore, right?
Yep. So that's the beginning of the weekend. And
I guess you do not celebrate Halloween in Singapore.
Well, it's not really that big of a thing here in Singapore, but there are some people who do celebrate, and they wear costume and all that.
Yeah, well,
but that's probably going to happen later tonight.
Yeah, that's right. It's a later this evening thing, something to look forward to, I guess. Yeah. Good. Okay. Well, would you like me to share my slides and share some science?
Absolutely.
All righty. All right. Let me see if I can do that here. Hopefully you can see that okay, nice and clear now.
Yep.
Looks all right. Okay. Well, thank you everybody for taking time in your Saturday morning to come and listen to this talk on coffee. It's really my pleasure. It's my first time speaking to a 100% Singaporean audience in the Singaporean time zone, so I'm very excited about that. I spent a fair amount of time preparing for this, looking up some of my old notes on the coffee industry in Singapore, and so I'll try and make references to the Singaporean coffee scene as I progress through the talk. Um, I want to first tell you a little bit about myself, actually, before we get into this. So I actually got my DNA sequenced, and my oldest ancestor, which is 60,000 years ago, this quote unquote Adam, if you like, is from here. Now this area, this spot is sitting right above sort of Ethiopia / Kenya, which is one of the birthplaces of coffee. So I've been as long as my genes have been on this planet, I basically have been involved in coffee one way or another. But of course, that was many generations prior to me. In my life, I've studied in a few nice places. I mentioned that I did my undergraduate studies at Monash University in Melbourne, Australia. And then I did my PhD at the University of Bath in the UK. This is a picture of Bath. Some of you may have visited this place. It was founded in the year 3, and it's a beautiful city. The Romans actually came here because Bath is named, as the name would suggest, after a natural hot spring they created a bath out. And this actual place was supposed to have special therapeutic properties. The water was supposed to cure certain illnesses, and bathing in the water was supposed to, relieve tensions and strains in your body. Today, you can still go and visit this location, and I strongly encourage you to do so. It's a beautiful piece of history, and it's only a 1-hour tour. It's a really nice thing to do. But after that, I moved to Boston, and I spent 2 years at MIT, Massachusetts Institute of Technology, where I actually worked in 3 research groups, 2 in chemistry and 1 in chemical engineering. And it was there that I began to understand sort of more context for where coffee and chemistry and all of these things that I learned over the years sort of fit together. But then after MIT, I applied and began my independent career at the University of Oregon. Some of you may be familiar with Oregon for its track and field and football team. We are the Oregon Ducks. This is one of our stadiums. But actually, Oregon is a big state school, which means that we are educating people in all the different disciplines that one might be interested in, ranging from political science. We've actually had 7 US governors come through the University of Oregon. Nobel laureates, those are in physics and chemistry. The Pulitzer Prize winners, so of course in writing. Rhodes Scholars, as well as then, of course, our athletes. The most famous athlete, perhaps, is Steve Prefontaine, who has basically pioneered long-distance running in the United States. And perhaps the most famous rich person from Oregon is Phil Knight, who is the owner and CEO of Nike. He continuously donates money to the university and actually has a very strong interest in science and technology. And so he's used his company and his money for very good, and because of him, we are able to perform world-class research. What we do in the academic system in America is I run a research group, and I don't actually do much of the research myself anymore. I help other researchers. And so this is my research group at the moment. In the top lines, you can see Jenna, Austin, Kwa, and Josh. These are my graduate students. They're pursuing PhDs. And on the bottom line, you can see my undergraduate students, ranging from we have Jack, Lily, Sarah, and Nicole. Sarah and Nicole were freshmen. They were the first year undergrads. And so some of you will be pursuing, hopefully going to university, and I encourage you to get involved in research early. And even if you're not going to university, you can still partake in research. And I think it's more of a way of life, right? It's learning to ask questions and find ways to get data to help provide an answer for you. So this is these are the talented people that do all the hard work in my group. Now, we are going to talk about coffee, but I do want to tell you what I actually do, okay? So this is a picture of the Earth's crust abundance of elements, okay? So basically what it is it's normalized to 1 million silicon atoms. So if I was to pick up a handful of dirt, let's say, you would find 1 million silicon atoms. You would also find 1 tungsten atom in that dirt. And you would find also 1 uranium atom in that dirt. And so you can see things that would fall above this line of 1 million to 1 as what I would call ubiquitous or common. So this green line, anything above. Anything below is pretty rare. And so it turns out, though, that most of the chemical industry uses catalysts, materials that make reactions go faster over a different energy trajectory. And they use these ones down here, the hard to find elements like platinum, iridium, rhodium. These are the things that you'd find in like your catalytic converter in your car. But nature can perform the same reactions using elements above the line. So instead of using platinum, for example, nature might go ahead and use something like photosystem 2, which is in the leaf. And so indeed, I'm interested in materials that fall above this line, but not based on enzymes. I want to do sort of earth abundant metal catalysis, but in designer materials. And so here's one example of the types of materials that I study. They're basically molecular sponges. They're very small. They have very small holes in them. And in this case, one of them has a nickel atom in it. And this nickel atom is capable of taking a small molecule of ethylene, which is just C2H4, and coupling it with itself. So in other words, making a dimer. So two of these add together. When you do that, you end up forming 1-butene. Now this compound 1-butene is a very valuable chemical feedstock for making plastics. And so being able to do this process where you take where you take ethylene and convert it to 1-butene is extremely valuable, both in the plastics industry, but also more macroscopically in the energy industry, because you're now using less energy to make something that is valuable. And this is all done over nickel. And so if you go back one slide, you can see that nickel right here is above this line of ubiquity. And so I'd say that we're doing something very positive here by using nickel rather than any of the precious metals. But that's not what we're here to talk about today. We're here to talk about coffee. And this is a very broad topic because we all know just enough about coffee that we have different interests. So I apologize already if I don't get to cover the topic that you want to hear more about. And instead, I've given you 4 links. Here you can go ahead and search on YouTube for each of these different talks that give you sort of a more in detailed discussion of water chemistry, freezing coffee, talking about particle size distributions and moving them around as you tap ground coffee and so forth. Please view these if you're interested in any of these topics in particular. Okay, in addition to that, I also keep a small library of interesting coffee-related papers. These are scientifically peer-reviewed articles that I did not write, but others wrote. And you can find this following this link here. Now, you could also just go to my website and scroll to the bottom and you'll find a link to it. But basically, it just contains papers, the year they were written, the journal they were published in, and then also what they're about, okay? And so like, for example, let's pick this one, 1990 Journal of Agricultural and Food Chemistry. And this is a paper about the Rio defect, which is a defect that some coffees experience that makes them taste kind of moldy. All right, so there's an interesting, interesting topic, a paper there. But if you come across a paper that is behind a paywall, please send me an email and I will provide the paper for you, okay? So let me tell you how my coffee journey began. As I walk into a cafe and I'm greeted by this board. And on this board, you see espresso coffee on the left and filter coffee or drip coffee on the right. And I'm also offered 3 different coffees. You can see a Brazilian coffee for espresso, Rwandan, and then below the writing there, you can vaguely see that's a Colombian. And on the right-hand side, we can see Mexico and Rwanda and Nicaragua. And so I've already learned that coffee is coming from different countries. But what I don't know is what these words mean: natural, washed, red bourbon, ruby variety. And I also don't understand what is giving rise to the flavor of fruitcake, brandy, and toasted seeds in this particular espresso shot. Is it that they've added fruitcake, brandy, and toasted seeds to the coffee? Or did they actually somehow magically make this thing taste like that, yet not containing those particular, food items? And so indeed, it's the latter. The coffee itself expresses flavors, but I don't know whether the flavors are coming from Brazil or whether they're coming from this particular farm or the variety or the processing method. And so this is the beginning of my journey, because I enjoy these coffees, but I don't know why. And so I'll frame it more simply, that the aim in the coffee industry, I should go back one slide, excuse me. On this slide, I want to point out that there's also a total range of flavors, ranging from toasted seeds and fruitcake all the way to lime, flowers, and blackberries. Okay, so I can see that somebody might want the one on the left a little more if they're interested in sort of like those deeper sugary flavors, and the one on the right if you like acids, right? So there's space for everybody to enjoy coffee. The challenge, however, is to find the coffees you like. And therefore, the challenge for the shop, the cafe, is to provide you with a good estimate of what you're going to drink. So if I told you that this cup of coffee should taste like lemon, bergamot, and watermelon, then you would hope that when you drank it, it tasted like lemon, bergamot, and watermelon, rather than somehow accidentally tasting like Brussels sprouts, dirt, and black licorice.
Okay,
And
that's
so
not
indeed,
pleasant.
this would be very unpleasant.
Yeah.
But you might actually like Brussels sprouts, Ferry, you might like Brussels sprouts and dirt and black licorice, but not if you were expecting lemon, bergamot, and watermelon.
Yep, yep.
And so indeed, this is the beginning of the problem. And so then you might ask, well, whose fault is this? Where can I understand where this chemically went wrong? And it turns out that about, I think, 50% of that variation comes from just the fact that the coffee is a natural product. It's a crop. And so every bean is different. And so, a very high quality crop, the beans are more similar to one another. In a lower quality crop, you have larger disparity of beans. And so about 50% of the quality of the coffee is coming basically from how high quality the green coffee is. But then you got to turn the green to brown, so you roast it. And so that's obviously important. But then I also think the brewing water is also important. So roast and water are basically equal parts, in my opinion. And then the least important component of all is the equipment. In other words, how you brewed it. Okay, and so it's easy to jump to say, oh, it's the barista's fault. It's the person who made it. Well, I call the human a piece of equipment in this case. So, so I'm going to say that that's a minimal piece. And I'm going to do my best in this talk to show you that there's a lot more that goes into the rest of this pie than this little piece of equipment. But let me show you why it's only 10%. It turns out that we actually grade coffee via a protocol called cupping. And the idea is simple. You grind coffee, you put it in a cup, you pour hot water on it, and then you taste it with a spoon over some period of time. And then you'll note then that there's no equipment at all in this process. It's just a cup that contains liquid and coffee, and that's it. And this is how we grade coffees, okay? Now you then could taste all these coffees and then grade them on a score sheet. You could assign a level of fragrance from 6 to 10 and flavor from 6 to 10 and so forth. And this would allow you to make comparisons between coffees. Or if you're more of an average person, you could just taste a lot of coffees and say which ones you like and begin to understand how, different processing methods give rise to flavors you like. But this is basically it. This is how coffees are graded, and this is how their value is determined, is through a standardized score sheet. Now, I mentioned that it's only 10%, and then you note that the brew method basically was free, right? It's a cup and a spoon, and that's it. But that doesn't have to be free. In fact, obviously, you could spend any amount of money on equipment. And indeed, I wanted to show you the most expensive piece of equipment I've ever seen in my life, which is a $1.6 million cup. This cup was designed by NASA so that astronauts can drink coffee in space. And here on the right, you can see Lindgren, the astronaut Lindgren, drinking in zero gravity coffee out of this vessel. Now, the way it works is that because liquids form spheres in no gravity, you put the sphere of liquid inside the vessel by catching it, and then the liquid will wet the inside surface. And because there's a capillary effect, in other words, this thin area pulls the liquid up to the lip right here, and then you can slurp it off that little space right there, and you're able to drink coffee out of a cup in zero gravity. That's pretty impressive. What do you think, Ferry?
Yeah, well, I mean, the one thing that catches my attention is the shape and the color of the cup, because
Yeah.
I wouldn't have
This is a
guessed
little-
that that's the shape that that is required for astronauts to be able to drink coffee. But I guess if it
the
works,
color,
it works.
I agree.
Yeah.
It works. Yeah, that's right. Well, the color is questionable, but yeah. So, but let's take a step back. Okay, let's go all the way back to the beginning and remind ourselves that coffee is indeed a plant, and plants that are grown in such large quantities often are traded and have commodity value. And so, indeed, coffee as an industry in the United States is worth about 1.3% of our gross domestic product. In other words, $225 billion a year is the coffee industry. This is a tremendous amount of money. It also employs 30 million people in the United States. And among other things, it basically is one of the main reasons that we have a tremendous amount of tax being paid because of people working in it. Now, within the industry, we also have two different types of coffees. I alluded to this earlier, that there's drip or filter coffee, which is a cup of coffee, and it's a much lower concentration, 1.2 to 1.5% by weight. And then you have espresso-based coffee, and that's more prolific in Europe and also in Asia. And you find that espresso-based coffees are much smaller, and they're about 10 times as concentrated. Now, it's not only in consuming places, for example, in Singapore, Australia, or the United States that it matters, but also in places that produce coffee like Burundi, where actually 90% of the people who live in Burundi work in the coffee industry, picking, growing, etc. And the coffee industry contributes about 25% of the gross domestic product in the country. So, coffee is a big deal for a lot of these producing countries. Now, it's not only Burundi, of course, Burundi is over here, but coffee is basically grown on the bean belt, which is anywhere near the equator that has relatively stable temperatures, warm temperatures, and high altitude. So you want to be growing Arabica coffee up high on a hill. And the reason for that is that you want to deprive the plant of carbon dioxide. Because if you give it too much CO2, you may remember from photosynthesis that CO2 turns into sugar, and sugar then turns into fruit. But coffee we don't want the fruit, we want the seed. So we don't want the fruit to form too quickly, and therefore we want to grow this at high altitudes. But there's another type of coffee as well, the Robusta coffee. Now these are very different plants. Basically, Arabica grows at high altitude and it doesn't produce much caffeine. Therefore, it's susceptible for bugs eating it, and so it's very difficult then to keep it, bug free.
So
caffeine is. Go ahead.
So caffeine has something to do with the fact that it's bug susceptible. Does that mean like caffeine has bug repelling property? Is that what happens?
Yeah. So caffeine is actually extremely toxic to humans and to bugs. It's just that we are much bigger than bugs. Yeah. So if you periodically you hear about somebody drinking too much caffeine and they pass and they die. And indeed that is a problem, but that's not a big problem because we're not, we're pretty strong. But a little bug doesn't want to eat much caffeine and it will die. And so Robusta produces a bunch of caffeine and it can then be grown at sea level and it's more hardy, it can resist bugs. But these are so different. Arabica has twice the number of chromosomes as Robusta. I mean, these couldn't be more different plants. Okay, so I told you before that we want to get the seed, not the fruit. Well, actually, coffee fruits and looks a bit like a cranberry. And if you were to crack it open and look inside, you'd typically find two seeds. If you find one, it's called a pea berry defect. So if you find two seeds, then you want to eventually remove the fruit so you get to the seed, because the seed's what you roast and then it turns brown and that's coffee, right? But it has to go from the left to the right somehow. And so that's called the processing method. If nature had its way, the tree would fruit, it would drop its fruit to the ground, or an animal would eat it, and then the animal eating it would remove the fruit from the seed, and you'd end up with this, or it would just shrivel up as a raisin on the ground, and that would be the natural process. So indeed, we still do something like that. We just have farmers pick ripe fruit, and then they dry them, and it turns into sort of a raisin, and then they squeeze out the seed, and that's called the natural process. The wash process is the exact opposite. You pick it ripe, and then you wash off all the fruit with water. And somewhere in the middle is the pulp process, where you basically hit the coffee with a pulper, like a hammer, basically, and the skin comes off. It leaves some of that fruity, sugary mucilage behind, and then you dry that in the sun. And all of those inevitably give you a green seed. Well, it is this green seed that then gets fermented for about 24 hours, sometimes less, sometimes more. And so hopefully then you can see that the natural process is basically like forming a raisin, and the wash process is cutting straight to the chase, getting straight to the green. Well, the natural process is typically favored in places that don't have a lot of access to water, things like places like Yemen, parts of Ethiopia, etc. So here's a picture of a drying facility in Ethiopia where you can see freshly picked coffee drying. And this is older coffee as it's getting closer to being dehusked. And so this is a natural process coffee that's been drying for perhaps 3 weeks. And in the background, you can see washed coffees drying after they've been washed. Now, one thing we do know about this is that this is fruit exposed to air. So something could go wrong. Fungus, bacteria, anything could happen to this. And we know that the seeds that have gone and had a bacterial or fungal issue tend to fluoresce. But we don't know why. And this is an open question, and understanding this would be very valuable and impactful to the coffee industry.
So
now,
so the fluorescing
ahead,
the fluorescing coffee is green coffee, right? That means it's unroasted coffee bean.
Unroasted.
Okay? So do coffee professionals, the coffee roasters, do they actually use this UV method to separate those bad beans? From the good ones?
Yes, they do. They
Oh,
sort
wow.
them. Yep. Yep. So you may remember then that previously I told you that the fruit has to start on the tree. You have to remove the fruit and then you have to ferment it for a little bit, and that is how you get to green coffee. Well, some of you might know Kopi Luwak or civet coffee is thought by some to be the best coffee in the world. This right here is a poo, and this came out of a small animal that feeds on the fruit of coffee. Now, this is definitely not, it is conclusively not the best coffee in the world according to those score sheets. And indeed, the best coffee in the world doesn't have a particular country dependence. It changes year to year. But I can tell you for a fact that the Brazilian, Sumatran, Vietnamese, and Hawaiian coffees typically score low on that score sheet because they don't have the acidity that people look for and value in specialty coffees. And typically Panamanian coffees, both natural and washed, are the high scores. Now, geisha here is referring to a variety of coffee, not the Japanese woman. So at this point, right, we've got coffee. It's green. It's been processed, either natural or washed. It's now green, and now we need to turn it to brown. And so that's called the roasting process. Okay, so fundamentally, roasting is just simply going from green to black and stopping somewhere in the middle. And as you roast coffee, at about 9 minutes, you start to hear an audible crack. That's called first crack, and that's where the bean releases water and CO2. After the first crack, the roaster then decides when to stop. When you get to full city plus, it cracks again. And then as you keep going, developing the coffee further, you get to something inevitably catching on fire. Roasters don't like to talk about that, though. They much prefer to show you roast curves like this, which is a measurement of temperature inside the roaster. And so the important pieces of this picture are that you start out with hot roaster, you dump in room temperature coffee, and so heat transfers into the coffee, and then you start heating it back up again. Now, after first crack, you start to develop the coffee. That's when the coffee goes from sort of a light yellow color to a brown color. And the darker the roast, the longer the development time, not the higher the temperature. So it's just somebody taking it out for a long time. But specialty coffees are typically only take about 10 minutes to roast. Now, actually, scientists have taken interest in this as well, because after you've brewed the coffee, you're left with some coffee waste. And in a recent publication in 2017, these authors showed that you could take this coffee waste and re-roast it, albeit under a special atmosphere of argon in the presence of zinc chloride at 800 degrees Celsius. But you then make this special type of carbon called N-doped porous carbon. And this material is actually known to be a good electrocatalyst, performing much the same reactions that you would have happening in your catalytic converter as platinum. So indeed, if you think back to what I'm interested in, trying to replace these precious metals with common elements like carbon, this is a tremendous outcome, because now we have our waste coffee performing the same type of catalytic activity as platinum. But it's, when you're roasting, you're forming a whole bunch of interesting stuff. Like, so there's not just one compound associated with coffee. It's not caffeine. You're generating thousands of different compounds. Here's a short list of about a quarter of the compounds that I was aware of. And I've taken these from 2 papers that were published in the 60s.
So I
show this only to demonstrate. Yeah, I show this to only demonstrate that it's complicated. Okay.
Yep.
And I often then get asked, does the concentration of caffeine depend on the roast? Okay, well, we know where caffeine comes from. It's produced by the plant. In a paper in Science in 2014, they showed this, okay? But that means that the amount of caffeine going into the roaster is determined by the plant. As soon as you pick it, it stops producing caffeine. So then the roast could very well be destroying caffeine, but the roast is also creating access to the caffeine. And so there's 2 effects. As you roast longer, you're going to create more access, but you're going to destroy more of it. But if you roast short, you won't have much access, but there will be a lot of it. And so as it turns out, the roast level doesn't really change the caffeine accessible concentration. It does change, of course, the flavors that you'll taste. The other question I get often asked is, which is more caffeine, espresso or a filter coffee? Well, here you can see the big bean regular beans having a cup of filter coffee, 16 ounces, contains 164.7 milligrams of caffeine. If you look at the big bean single espresso shot, you can see it only contains 75 milligrams of caffeine. And even if you add the double espresso shot, you're still only getting 140. So indeed, you actually need to drink a fair few espressos to get the same amount of caffeine as you would from a cup of filter coffee. But it's not useful to talk about molecules and flavors. It's much easier to simply say words that we might have relationships with. Like, for example, I might describe a coffee as having a pineapple flavor, and you might taste it and say, no, Chris, it's not pineapple. It's more like a grape. And this is where the interesting aspects of the coffee industry come in, because now we're relating words to chemistry and experiences. And so the specialty coffee industry has developed this flavor wheel to help us all speak the same language. And if you go around the outside of the flavor wheel, there's going to be reference ways to prepare apples, so that, Ferry, for you and I, perhaps we have a different relationship with apple. But we could prepare this standard definition of apple, and we could then reprogram ourselves to call that flavor and that smell apple. And this is an exercise that I do with my students sometimes to teach them the various different flavors. Okay, but we don't know what flavors are in the coffee. We know we've roasted it, but the only way you're going to know what's in the coffee is if you actually brew it. In order to brew it, you've got to grind it up. So fundamentally, what you're doing is taking whole beans and turning it into dust. But where you stop, how fine you go, really depends on the brew method. Now, I don't have time to talk about all the brew methods today. Instead, I want to focus on the fundamental science. So basically, what I want to impart on you is this way that we measure the size of the particles that come out of the grinder. So independent of the grinder that you use, we can put these particles into a device called a laser diffraction particle size analyzer. These particles get broken up into, so they're flying by themselves, and they pass by a light source. And then you can think of this diffracted light basically as how big of a shadow did this thing cast, and the larger the diffraction, the smaller the particle. Okay, and so that's one way of doing it. Another way is to use a scanning electron microscope, and here you can see we've sputtered this coffee in gold so that it conducts electricity, and then we've scanned it, and you can see some dense regions off to the sides, and you can see some holes in this really large piece. And if you zoom in, you see actually that these are relatively small pieces, 10 micrometers, 10 to 50 micrometers across, and they're pretty dense. And indeed, coffee is pretty dense. But the real question then is, what shape are these coffee particles? How do I describe them? And that's actually basically asking, what is the size of this sea urchin, right? Because actually, of course, one might say the sea urchin is this big. The next person might say, no, it's this big. But of course, the sea urchin is actually this big, right? And the laser diffraction method is doing us an approximation like this. And the reason is that it's just taking the diameter that it sees, okay? And so so of course, that's going to overestimate the volume contained within the coffee and underestimate the surface area, but it's the best we've got. And according to this paper, the spherical approximation, as we get from the laser diffraction method, is actually pretty good when you grind pretty fine. And so as you grind coffee, the approximation of a sphere becomes better. Now, you saw some holes in the coffee in that SEM image before. Well, you might remember back to the very beginning when I told you I work in material science with these materials that have micropores, these really small atomic-sized pores. We can assess how small those holes are by pumping nitrogen gas into these holes. And basically, at liquid nitrogen temperature, the nitrogen will condense, and we can then measure how much nitrogen is inside the material. So a material like these catalysts that I was talking about at the beginning can absorb about 1 milliliter per gram. Sorry, excuse me. I should rephrase that. 1 liter per gram, which is incredible. So they're very porous. And roasted coffee absorbs about 5 milliliters per gram. In other words, 7 milliliters per gram. In other words, it's not porous. And so the hard spherical approximation is a good approximation for what's coming out of the coffee grinder. Now, this is the output from those laser diffraction methods. So on the top, you can see if you just count the particles as they fly by, most of the particles are dust. But if you then normalize that by surface area, the big ones are really big, so they have a lot of surface area. And so you can see here, there's about 15 to 25% of the surface area comes from the big pieces. But then if you normalize by volume, well, the big pieces occupy a lot of space, so they take up a lot of volume. And so actually coffee grinds, you typically see this sort of curve with a large peak here for the big pieces and then this tail here for the dust. And we can understand where this comes from. Basically, the big pieces sizes are determined by the grinder, and the dust comes from every time you have to crack the big pieces to get them small enough to leave the grinder. And so the dust doesn't change size. You just make more dust the more fine you grind, right? So the big pieces get smaller, and the dust increases in size. And this grind profile actually follows the exact same grind profile that one might see for a volcanic rock exploding, which is pretty neat. And you know, apparently these mathematicians have demonstrated this exact shape particle size distribution. Well, I told you just then that the dust doesn't change size. You see, it's just going up or down in volume. The only way you can change the dust size is either by using a different grinder, but even then, that doesn't really do it. What really does it is temperature. And the reason for that, well, I mean, first let me show you. As you cool the coffee down and grind it while it's, you know, dry ice temperature and then liquid nitrogen temperature, that the particle size is going from about 22 microns, about 18 microns down to about 10 microns, and that's making a really big difference. And the reason that this is happening is because we can think of these as atoms in space. And if I were to put a crack through this material, the crack wants to go in between the atoms. You can't crack an atom in half, so you're going to go between them. But at low temperature, all these atoms are not moving much, so the crack can find a way to the other side. At higher temperature, the atoms are moving all over the place, and so the crack meanders. It takes a while to get to the edge. And so what we learn from that is that cracks propagate faster at low temperatures, typically, and they also typically take more regular cracks through the material, and so that gives rise to a more regular grind profile. In addition to having a more regular grind profile, you also get the benefit when you cool coffee down of it basically increasing its shelf life. According to the Arrhenius equation, about every 10 degrees Celsius that you cool something down, the chemical processes that are occurring go about half the speed. So if I go from 20 Celsius down to freezer temperature, which is minus 20 Celsius, most of the chemical processes are occurring at 16 times slower. And so you basically can prolong the life of your coffee a very long time by cooling it. And there have been people that have rolled out industrially freezing coffee. So this is a cafe in Portland, Oregon, where they have their coffee in freezers above their grinders. And in Australia, there's a cafe that stores all of their coffees individually dosed, and they're all pre-packaged in a freezer, and they're grind on demand for somebody who wants to come in and experience these lovely coffees. Okay, so we've got the grinding under control. We've got it brown. We have a good coffee picked out. Well, we need to do the water, okay? So a very quick crash course on water chemistry is that water is polar. It has a partially negative and a partially positive charge, and the H's are plus and the O's are minuses. And they arrange such that the O's point towards the H's. Now, on a really small scale, you can have these form these little hexagons. And indeed, that's why snowflakes have 6 sides, is because water, when it crystallizes, forms hexagons. So on the molecular level and on the macroscopic level, you can see that. But water also can solvate other things. So you can have a positively charged species like calcium, and it'll be surrounded by the O's. You can have a negatively charged species like chloride, which will be surrounded by the H's. And therefore, you end up with, you end up with water solvating minerals. But additionally, you can also solvate octane. So this is a non-polar species, and by water forming cages around it. Now, this is really unfavorable because water then has to be ordered, and water hates being ordered. So the limit of solubility of oil in water is pretty low because of that. You can also dissolve carbon dioxide. But let me summarize this for you in a more simple way of how it impacts coffee. The positively charged minerals in water are the flavor extractors, because they come along and find molecules like theaflavin that taste lovely like black tea, and they will temporarily bind to those oxygens, pulling that molecule out of the coffee and into the water. But the positively charged things will not interact with molecules that are hydrocarbons because there's no polarity. So indeed, this compound, alpha-pinene, imparts the chamomile flavor from chamomile tea. And so hopefully you can already see there's a problem, that the water you might use to brew coffee is not the same as the water you might choose to brew tea. All right, so you've got the cations that are going to pull out the flavors from the coffee. Then the anions, their job is to structure that flavor. And the most important anion that we'll talk about is bicarbonate. So basically, bicarbonate can deal with acids by receiving an H plus, turning into carbonic acid. It can lose its own H plus and turn into carbonate. And therefore, this species, bicarbonate, basically acts as a relay in the presence of acids. So if I had something like vinegar and I poured it over bicarbonate, some of you may have done that experiment where you take baking soda and mix it with vinegar and it makes bubbles. And the reason is the vinegar is acidic, so it reacts and pushes up this direction. This compound, carbonic acid, is unstable and decomposes to form carbon dioxide, which is a gas, and therefore it bubbles. So you might remember then, if you mix vinegar with bicarb, you get bubbles. All right, and if you go the other way around, you head this direction. Okay. So you remember the flavor wheel then, and I showed you that these are all the flavors that one might be able to perceive in different coffees. If I change the level of bicarbonate in my water, I can turn off the acidic panels. Now, this is not a good thing because we like acidic panels in coffee. And so indeed, the higher the levels of bicarbonate, typically the worse your coffee is going to taste. But at the very beginning, I told you that the Brazil, Sumatran, Vietnamese, and Hawaiian coffees are typically not very high scoring coffees. They're not the highest profile coffees because they don't have the natural acids. But that is a good thing if you don't know what your water chemistry is, because you wouldn't be able to taste them anyway in a water that had a high level of bicarbonate. And indeed, these coffees typically have these flavors of chocolates and sugar and so forth. And so these are if you like low acid coffee, I'd encourage you to try pursuing these different origins. Now, let me summarize all of water chemistry in one graph. Basically, you don't want to have too much bicarbonate because that will cause no acidity in your coffee. But if you have too little, you end up with sour coffee. And you don't have too much calcium or magnesium, the flavor extractors, because if you have too much, then you start extracting weird stuff that you don't actually like in coffee. And if you don't have enough, then you don't extract enough flavor. So somewhere in the middle is where you want to be. Okay. And there's not one ideal water. And so I've summarized a few places. So if Singapore is kind of like Melbourne, pretty soft down here at the bottom. Places like Berlin are sort of in the middle, and then Los Angeles is pretty hard. It's even harder than that, actually. It's a little higher. And I've shown you how, if you wanted to make your own waters, you could take deionized or distilled water and mix these chemicals in there, and you'd be able to access different water brewing. And you could taste the differences by brewing coffee in these different water locations. But the most important thing is just to simply note that water chemistry makes a big difference for flavor, right? That's the key thing. And so you don't even need to make your own water. If you want to try the experience, you can go to the supermarket and flip a bottle of water around, and hopefully it'll tell you what's in it. And in this particular case, this bicarbonate concentration is 153 milligrams per liter. If you look back on my graph, 153 milligrams per liter is off the chart.
It's that's a lot of bicarbonate. Yeah.
It's going to be terrible. So if you ever want to try brewing with hard water, go find Evian, put it in your kettle and brew some coffee and see how you think it tastes. It's going to be very unpleasant. Now, cast your mind back to the very beginning of the talk. I told you that the Romans went to Bath because they thought the water had therapeutic properties. Well, indeed, the water in Bath is special. It's extremely hard. It has very high levels of calcium, 400, and very high levels of sodium at 200, bicarbonate at 151. But the really unusual thing here is sulfate, SO4. Now, this should have a 2- because this wasn't written by a chemist, as you can tell. But with the 2- there, this species is in extremely high concentrations. It turns out that the World Health Organization states the upper limit for sulfate for safe water is 250 milligrams per liter. So this is in excess of 3 times that. And what happens when you drink sulfate-rich water is the sulfate stays in your digestive system. Water moves from inside your body to inside your intestines, and you get diarrhea. And so indeed, I think the Romans probably did find therapeutic properties drinking this because they drank it and it made them go to the bathroom. And I would say it's a miracle, all right? So we've done all that now. We've got the water, the roasted coffee that's all ground up. It's now time to brew a little bit. Now, I don't want to talk to you too long about this because there are so many different brew methods, and this is kind of the fun part in coffee, the experimentation and the romance. So I want to just show you some of my most recent work, which was aimed at developing a better understanding of what happens at that moment when water touches coffee. And so we develop a model where we start to fill up like an espresso basket full of fake particles that, little ones and big ones, much the same as the grinder would produce. We have the variables that you'd normally expect, like the amount of coffee in there and the radius of the basket and so forth, and the pressure and everything like that. Now, the challenge, however, is how do you quantify a success? How do you quantify what's coming out of the coffee, right? How do you know, in a model, you need to have some metric for is it extracting? And it turns out in the coffee industry, we borrowed a technique of measuring what's been extracted by using a measurement called the Brix measurement, which is simply a measurement of refractive index. And it works really well in wine because wine is 15% alcohol. But before it was 15% alcohol, it was 15% sugar. So I could monitor the change in sugar to ethanol by looking at difference in refractive index. And a patent published in, I don't remember, showed that you could relate refractive index and temperature, so X being temperature, Y being the refractive index, to a concentration, the percentage of total dissolved solids. Now, total dissolved solids is the total mass of coffee that's solvated in the cup divided by the mass of the beverage. So if I have a 100 milliliter beverage and it contains, let's say 1 gram of coffee, then that would be 1% total dissolved solids. The extraction yield is slightly different. That is the mass of coffee that ends up solvated in the cup relative to the mass of coffee you use to brew it. So for example, if I use 20 grams of coffee to brew, and then I only ended up extracting 2 grams of coffee from that 20 grams, that would be an extraction yield of 10%. And so these two are related to one another in the sense that if you extract a whole bunch of stuff and you use a little bit of liquid, then the total dissolved solids will go up, right? Because it's getting more concentrated. But you could still under extract by using a bunch of coffee and then making a really dilute cup, and that would put you over in the bottom left of this chart. And so indeed, we've empirically arrived at this idea that if you extract somewhere between 18 and 22% of the mass of coffee, and it ends up being somewhere between 1.2 to 1.4% by mass in the cup, that this will probably be a tasty cup of coffee, okay? But the problem is that the refractive index of water is 1.333 at 25 degrees Celsius. And these 3 different compounds, sodium chloride, sugar, and ethyl acetate, all change the refractive index of water differently. So for example, this is the refractive index here, and this is the weight percent. I can add 5 times as much ethyl acetate as salt and get the same refractive index, which means taking a refractive index measurement does not help us understand whether the coffee is going to taste more salty or more ethyl acetate. You simply can't know. Now, you don't want it to taste like either of those things, and it probably won't. But the point is that it's not really telling you about any flavor. It's just telling you about mass. In addition to that problem, what you extract, the ratios of what you extract depend on temperature. There have been several Nobel Prizes in chemistry in 1901, 1902, and 1904 related to the kinetics of extraction, kinetics in general, that demonstrated basically that the equilibrium constant, so if you let something go for a very long time, it would reach equilibrium, depends on temperature. And so I can show that very clearly here, that if I brew coffee with 20 degrees Celsius water, I only extract about 9 milligrams per gram of coffee that I used. But if I use 90 degrees Celsius water, I can extract about 15 milligrams per gram of coffee I used. In other words, I can get about double the caffeine concentration by using roughly boiling water, and cold brew has way lower caffeine. But the weird thing is that caffeic acid, this compound here, gets fully extracted independent of the temperature. So hopefully you can then see then that the ratio of caffeine to caffeic acid will change the way that you perceive this coffee, and temperature controls that. And so indeed, that's a bit of a problem for using refractive index measurement, because you're changing the populations of these compounds relative to one another. But nonetheless, it's still the best thing we've got, this refractive index measurement. And so that's what I use in my studies for now. And basically, I can parameterize my model simply by saying there is only one coffee compound, even though we know that's not true. And it has a diffusional coefficient of this. And you can see that this carries the units of meters squared per second. And so that's saying the surface area per second, that's how far, basically this stuff is moving into the water. And then there's a rate law, K. Now, formally, the K should not have any units. And if you take any physical chemistry, you'll realize that they have no meaning here. But this is simply telling us something about the rate in which extraction occurs. And together, I can begin to predict extraction yields as a function of grind setting. And so that's basically where my work has got to now, is being able to say, if I use 16 grams of coffee and I grind it at this grind setting, I should be able to predict the flavor or at least some property of this coffee. And it works pretty well. So I want to leave you with 3 take-home messages and then have plenty of time for questions, because I'm sure that we're going to have some discussion. But the first take-home message is that bicarbonate, that buffer in water, is very powerful because it kills the flavors of acids. We don't want that in specialty coffee. We would much prefer to have the acids there. And so in hard water locations, it's typically, we tend to want to make smaller drinks so that there's less bicarbonate in there. And so indeed, hard water locations tend to favor espresso. Secondly, as you grind finer, you now may have realized that you make the big pieces smaller, but you make the small pieces have higher population. And so when someone's trying to describe to you what grind setting to use to optimize that flavor profile, it turns out that's quite complicated. And so you shouldn't feel really bad if you're having difficulty dialing in a coffee and making it taste good, because these two things together are they're extremely important variables. And then finally, I want you to remember that actually at the end of all of this, the most important thing to do is to have a good time while you're drinking coffee, embrace the variety of flavors and the variation that you get in year to year and cafe to cafe, and to actually taste your coffee. And so with that, I wanted to actually point out, now I have no affiliation with any cafe in Singapore, but I do remember when I originally wrote the book Water for Coffee, one of the first orders that I ever received when we were selling that book was to a cafe in Singapore called Pacamara. And so I encourage you, if you're interested in going and tasting a specialty coffee, I suspect that Pacamara in Singapore would do a pretty good job. I don't know who purchased the book there. I don't even know if they work there anymore, but I can tell you for sure, if you go in there, you're going to have a good time. With that, I want to just thank a few people. That most of this work is done by volunteers, baristas that have donated their time, their expertise, their knowledge, and taught me a lot about coffee. Also, roasters that have donated me coffee, which is pretty valuable stuff. So I'm really grateful for all of these people shown in the middle. And then the academics. So Jamie and William and Justin are all actually in mathematics. Zachary is here in Oregon, and in Washington, excuse me, and he's a chemist. And then a few other chemists as well. But I really want to emphasize actually on this slide that coffee is an inclusive and fun area to work, because you can, collaborate with people all over the place in all the different disciplines. And so I'm really grateful to have had an opportunity to work with all of these people, and for the equipment manufacturers who have donated their equipment to me very generously so that we can achieve some of this work. And I also want to thank all of you for listening in. And Ferry, thank you for hosting me today. And I'll happily take any questions.
Yep. Thank you, Chris. Well, I mean, I certainly learned a lot from listening to you. And in fact, we actually do have some questions. Shall we go and answer some of these questions?
Please.
Okay. So the first question that we have here is from Raj. His question is, why is coffee so special? Isn't it just a drink? And what is so special about coffee that makes it almost like a religion?
That's a great question. So coffee is quite special in terms of drinks, because if you think about all the drinks that you have in your life, Coca-Cola, beers, wines, whatever, most of these drinks come ready to drink. You don't have to add any water to it, right? And so they're already complete. But coffee and tea are unusual in the sense that you still have to add water. You have to brew this thing. There's an art and a craft, and obviously a science, as I have just demonstrated. But that means that there's many places along the way where you can make decisions, scientific decisions. That's not true at all for those other drinks that I mentioned. Those other ones, you simply drink them. So when you make the comment, is it somewhat almost like a religion? I understand, because people have rituals. They get up in the morning, they do their process. They make that cup of coffee that wakes them up, and they have this whole experience. And indeed, that's part of it. And that's part of the reason it's so fun, because you can have that interesting experience. But actually, that's not the main reason that coffee's different. The main reason it's different is because it's, as I mentioned, one of the only ones where you have to make a decision about the grinder, the origin of the beans, the amount of water you use, the amount of coffee you use, the amount of time you brew it for, how you brew it. All those things go into this process, and that's just really unusual for such a large scale beverage industry.
Wow, that's an interesting way to look at it, I guess. So I guess everyone who takes their coffee seriously will have their own so-called ritual of how they prepare the coffee, right?
Right.
Okay, so we've got another question here from Jen. Her question is, are the flavors of coffee perceived, or are they real?
Jen, that's a good question. Somewhat philosophical, in the sense that the molecules that you are tasting are indeed molecules that exist in coffee. They are there. And what you are tasting and then thinking of when you taste these molecules, for example, I drink a coffee and I'd say it tastes like lime. that may or may not be the same molecules that show up in lime, right? It may just be that you're perceiving them like lime, but they could be different. We actually don't know that. We have no idea. We don't have an answer for this. And this is what makes it really interesting, is that there's so much interesting chemistry, but then also sensory science, and then also linguistics, thinking about how to describe these flavors that make that, that bring us all together. So is it real? You're having an experience, yes. That's definitely true. And the chemistry is impacting that because these molecules are binding to receptors in your mouth. But is it exactly like a lime? I don't know. I need to think about it.
Well, I guess the way I usually explain this to my student is that, so sometimes, like, if you buy a bag of coffee, sometimes it say things like, oh, it has a notes of blackcurrant, for example. To someone who tastes blackcurrant often, you might tend to agree with that description. But for someone who have never tasted blackcurrant before in their life, they would have no idea how it's supposed to taste like. I mean, you're probably tasting the same thing, but you would describe it in a different way because you have no
exactly.
Yeah.
So that's the challenge, is that you and I may have not aligned our flavor preferences or our experiences, and therefore you might say blackcurrant and I might say blackcurrant, and I might actually mean clove and you might actually mean grapefruit.
Definitely. Okay, so next question from Sophie. Do people get jobs as coffee graders? I guess maybe an extension to this question would be, sorry, Chris. If let's say the extension to this question, maybe it would be, if let's say I want to get into coffee industry, what sort of job could I be in the lookout for?
Yeah. So first of all, to directly address the question from Sophie. So that basically, yes, grading coffee is something that you can actually get trained and qualified to do. You typically would go through the CQI, which is the Coffee Quality Institute, and become a Q grader, which is a quality grader for coffee. This process does cost money. It's like becoming a sommelier for wine, but it imparts you with a skill that then you're able to taste coffee and objectively score them on that score sheet, so that you can actually then assign value to coffee. So then you would be hired by companies that are roasters, green importers, etc., and you're worth money to them. But as an extension to that, you were asking generally about how to, what jobs, basically, how do you get into the working in the industry, and yeah, basically the short version of that is that I think you should be trained in a classical science, a classical discipline, like, for example, chemistry, biology, physics, mathematics. Not trained in food science, because then you'll be narrowed down into only being taught what is known about food, not what is not known about food. And what you want to know is what is not known about food. And so you need to have the fundamental toolbox to go after those problems. So if you are interested in becoming a coffee grader or something, you should get the qualification. But in addition to that, I'd encourage you to pursue a natural science, or just any training for that matter, even if it's in global policy or whatever. And then go from there.
Okay, thank you, Chris. So maybe we have, okay, there's another question here from Jenny. Her question is, if I use bad coffee and add vinegar to my coffee, I guess to increase the acidity, will it then taste good?
No. It'll taste like vinegar. So the reason that the answer is obviously no for that is not because it's a bad idea. In fact, adding something to your coffee to make it taste a certain way is something we do. We add milk because we like the flavor of milk plus coffee. Like we do this. The reason is that any acid that's in coffee, if you picked a certain acid that you might find in coffee, the concentration of that acid is extremely low. So low, it's not even one drop. It's much less than that. And so indeed, actually, by adding any amount of vinegar that you could ever imagine adding, you would have added way more vinegar than any of the other acids that you could possibly imagine would have existed in there. And so adding maybe the world's smallest amount of vinegar, like we're talking like, a microliter, maybe, but even then, I think that that's probably too much.
That's
Yeah,
true.
that's fine.
And I guess not all acids are equal in terms of coffee, because like you have other acids, because vinegar is acetic acid, and I would think that you wouldn't want that to be in your coffee, right?
No, citric acid, for
Citric.
example, is a valued one.
Yep.
Chlorogenic acids are valued exactly. Yeah.
Yeah, definitely. Okay, so then there's one more question here, and then after that we'll we'll end this session with another question. Okay, question from K. I would think that the finest grind will get the best coffee since the surface area is higher. So
Right.
shouldn't we just go for the finest grind?
So you have two problems with that. So it's good thought process. The finest grind does give you the most surface area, so you do get more out of your coffee. But if you remember back to one of my slides, I said that we don't actually want to extract more than 22% roughly. Things start tasting bad because the remaining percentages are all compounds we don't like the flavor of. So if you grind fine, you do get a whole bunch of stuff. You get a lot of coffee out, but you also get flavors you don't like. In addition to that, it's very difficult to separate water from really fine coffee grounds, right? So we have one way of doing it. It's the espresso machine. But if you try and put really fine coffee grounds into a French press or a cafetiere, or you try to do a really fine grinds in a pour over, you'd know then that the water doesn't really go through the pour over all that well. And in the French press, oh, it's a disaster. I mean, you plunge it and all the coffee comes everywhere, right? So that doesn't work out very well. So you're not wrong thinking that you want to grind finer because that makes it more efficient for you to basically get more out of your coffee. But there's a tipping point. At some point you grind too fine and everything's bad.
All right. So all right. Let's end off with this one last question, and it's actually from me. So if I'm someone who wants to take his coffee more seriously, what would be the first step to the right direction? What is something that I can do today?
Something you can do right now? Yeah.
Yep.
So first thing you can do is go on Google and Google specialty coffee in Singapore, and then go out and go experience those coffees in the specialty coffee shops around town and see what you like and see what you don't like. Once you have an understanding of what you like, the next thing you could do is worth, if you're going to spend any money, it's worth spending the money on buying a grinder. Now you don't need to spend too much money, about $100, but a grinder is extremely important. But then after all of that, I think actually probably the most simple thing that one could do is just having a scale, having a balance to weigh the amount of coffee you use and weigh the amount of water. So independent of your grinder, I mean, you can still brew coffee with a bad grinder. Okay, you can even buy pre-ground, but as long as you're being reproducible, using the scientific method, that's how you really improve your coffee, is to make sure that you're doing things systematically and only changing one variable at a time.
Wow. Okay. I guess yeah. Some of the audience might start doing that after this. So well,
So.
unfortunately, that's all the time that we have for today. Thank you so much, Chris, for being here with us and sharing with us your expertise, experience, and knowledge about coffee. I really learned a lot from listening to what you have to say.
Well, thank
And
you for having me. Thank you.
yeah, so to all of you, the audience, okay, thank you for tuning in, and remember to hashtag UntameSG in your social media post. And the names of all the lucky winners will be posted on our Untame Facebook page. So keep a lookout. And when it comes to STEM, nothing is beyond boundaries. Thank you so much, everyone. Goodbye.